All right, so the last few days, what we've been talking about as far as circles are concerned is we've been talking about angles with respect to circles. We talked about central angles. We talked about what happens, when two segments intersect inside a circle, on a circle, outside of a circle. We talked about the angles that are created from that, okay? Well, now we're going to kind of change gears a little bit, and we're going to look at what happens to the actual segments, okay? Now, to understand this part, for what happens inside of a circle. So we're going to look at that first. And realistically, the only types of segments that can intersect inside a circle are chords. Okay, so this is really going to only apply in one case. Okay. So before we really kind of get started, what I'm going to do is I'm actually going to create these triangles. Okay, in order to see kind of where this comes from. So in this circle, we have chord A, B, and chord D, C intersecting at point E. And you can kind of, or hopefully you can kind of tell that, yes, the chords are not congruent, okay? They're slightly different sizes because the truth is we want to look at what happens for any general case, okay? So when we look at this, what I just kind of created was two triangles. And we can see that this angle right here, angle A, intercepts arc BC, okay? So does this angle right here, meaning that we have angle A and angle D essentially congruent, okay? I am supposed to be screen sharing, and I keep forgetting to do that. I'm awesome. Thank you guys for reminding me. Okay. All right, sorry. Moving on. So we have angle A and angle D essentially here are congruent because they intercept the same arc, okay, and they're both inscribed angles. Okay. Now we also want to look at this angle right here and this angle right here. We know that those two are congruent, right, because they're vertical angles. So essentially what we have here is we created two little triangles, right, and we just showed that they're similar. Now, that doesn't necessarily mean that they're congruent. Can they be? Yes. Are they absolutely? No. Okay. All we've proven so far is that we have triangle AEC is similar to triangle DEB. That's all we have so far. Okay. Now, utilizing this, we're going to actually take a closer look at what happens to their segments, to the segments, by examining the similar triangles and understanding that the sides are proportional, okay? So what that means is, if I look at AE, right? Sorry, it should be AE. If I look at AE, right, and how it relates to DE, it's going to equal the same ratio if I look at EC compared to EB. Okay? And that's just using the idea of similar triangles. Okay? Now, from here I'm going to apply the cross product property. Right? And what we have here when I do that is I get that AE times EB is going to equal DE times EC. Okay. And again, these are segments that have nothing to, so even though we put these lines in there, realistically these had nothing to do with our end result, these little segments right here. So essentially what we just showed is that if I've got two chords which intersect inside a circle, right, then if I think about the individual pieces, right, if I multiply the pieces together, right, I should get the same result for each one. Now, it doesn't mean that each of the segments are congruent or anything like that, but what it means is if I take the product of AE times EB, right, so the little two pieces of the chord, and I multiply it, and then I also look at DE times EC. If I find the product of those, it'll be the same. Okay? So essentially what we're also saying in here is that the chords cut each other proportionally. Okay? And we'll look at some examples of that in just a few moments. Okay? But that's what I'm calling the segments of chords theorem. Okay? Two little pieces, okay, multiply together. Okay? Now we're going to look at, so that was in, oh sorry. Oh yeah, so sorry, I apologize. That's really the only case. So now what I'm going to look at is a couple of examples. I think I had more, right? Oh, that's it. Okay. We'll look at two examples. In example 1, we're going to solve for x, okay? So what I'm going to do really quick, though, is I'm going to, just to help us out here and understand how to apply the formula, I'm just going to assign little points. So I'm going to call this A, E, B, and this is going to be C, D, okay? And now, the formula that we just talked about says that if I take this guy, AE, and multiply it with EB, I should get the same result as when I multiply DE times EC. Okay? And that's what this theorem tells us. Okay? So now we want to look at what the pieces are, and then we can substitute since we know what their values are. So since I know AE is 15, EB is 8, if I multiply those together, that should give me the same thing as multiplying DE, which is 10, times EC, which is X. Okay? Now when I multiply 15 times 8, what's 15 times 8? You guys have a calculator in front. Use it. 120. Okay? So I know that 15 times 8 is equal to 120, and that's supposed to be equal to 10 times x. So now to solve from here, just divide both sides by 10. I get, sorry, I should write that in black. I get x is equal to 10, oh, sorry, not 10. X is equal to 12. Okay. And again, we're going to check this just for the sake of it, but I mean it's pretty straightforward from the way that we solved it that this should be true. But again, we're going to plug it back into here. And so what I have is I need AE, which is 15, times EB, which is 8, and that needs to equal 10 times what we said X was, which is 12. Well, 120 equals 120, so we're good. Okay. Again, sometimes for very simple problems, checking is just kind of mundane, but we got to do it. Okay. All right. Next problem is going to be significantly more difficult. And the reason I'm doing this is because I want you to see a very complicated problem that involves this stuff. Okay? So just like before, I'm going to label my points. I've got A, E, B. Let's just call this C, D. Okay? And again, so just starting off the same way, right? The segments of chords theorem says that if I take AE and I multiply it with EB, that should give me the same thing as if I take DE and multiply it with EC. Okay. Now I'm going to enter in the values, or sorry, substitute in what I know. I know AB or AE is x plus 1. I know EB is 2x. And I know DE is 7. And EC is 16. Okay. So let's just look at the right side first. What's 7 times 16? 112? Yeah. I don't know why that's black. 112. And then what about the other side? All right, so this is kind of like a little bit of algebra review here. Remember, all right, that if I have some quantity x plus 1 and I'm multiplying it by some value, right, I have to distribute. Right? And then tell me, what is 2x times x? It is not 3x. It's 2x. 2x squared. If I take an x and I multiply it by an x, that's x squared. Okay? So 2x times x will give me 2x squared. And then I still have to distribute. And 2x times 1, so it would be plus 2x. Okay? So this is where we kind of start to run into problems. Okay? What type of equation is it? Sorry, what type of equation is this? Who knows? Who remembers? All right, this is what we call a quadratic equation. Okay? And all quadratics have the form ax squared plus bx plus c is equal to 0. Okay? That is the quadratic form. So just really quickly looking at this, at our problem, do we have it in quadratic form yet? What do I need to do, Alana? Sorry, say it again. Okay, so I can't just remove the square root, right? So that's kind of the difficult part about solving quadratics, is that square root makes things, or that square makes things so much more complicated. Okay? So the first thing I need to do, though, is I need to get it into this form, right? What do we notice about this form? What's it equal to? It's equal to 0. Does this one look like that? Does our problem look like that yet? What do I have to do, Chris? Perfect. I have to move the 112 over to the other side by subtracting it. So what I'm left with, and I'm going to use a different color for this system. I'm left with, I'll use orange. Yeah. 2x squared plus 2x minus 112 is equal to 0. So now I've got it in quadratic form. Okay? Now, there's two different ways there's actually several ways that I can solve a quadratic, but the two ways that you hopefully learn or hopefully remember from Algebra 1, and again, if you don't remember or anything like that, I know this is a COVID year, this is why we're doing this, it's kind of a reminder. There's two different ways. The first way is to solve by factoring. Okay? The second way is to solve by using the quadratic formula. Does anyone remember what the quadratic formula is? No one does that song? Okay, that's fine. So remember, the quadratic formula says in order to solve x in this case, right, given that it's in this form, right, it would be negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. Okay. Now that one's pretty complicated, right? That one's pretty complicated. Okay. So we're going to do factoring first, okay? And factoring, I'm going to move this over here. We're going to try factoring for, oh, please do not do this to me. Okay. All right, factoring, there's kind of different ways to think about it. So factoring essentially, right, first thing I want to look at is factoring out the greatest common factor, okay? And so kind of just to give you a little understanding, if I go, let's just say A times B plus C, right? If I multiply that out, this gives me AB plus AC. For whatever reason, we call this the distributive property. But when we factor and go the other way, if I have some AB plus AC, right, I'm going to say that this is equal to A times B plus C. All right, when we go the other way, it's called factor. Okay? And that's one method of factoring. So the first thing I want to do is I want to look at is there a greatest common factor between all of these parts? Well, all of them are divisible by what? Two, 2x, and 112 are all divisible by what? 2. Right? Now that would be the greatest common factor, so I'm going to factor out the 2. So I factor out the 2, and I'm left with x squared plus x minus, what's that, 56? That's equal to 0. Now the reason why I do this first, okay, factor out the greatest common factor, is I basically simplify the problem before it really starts, okay? And, right, I'm allowed to now divide this entire thing by 2, provided I divide this whole thing by 2. Well, what, on the left-hand side, this gets rid of, but what happens on the right-hand side? Nothing. It's still 0, right? So that's the beautiful thing about having a quadratic equal to 0 is when I start dividing out like common factors, right, I'm literally just getting rid of them. They're just gone, okay? Because 0 divided by any number is still going to be 0. So I've simplified the problem to x squared plus x minus 56 is equal to 0. Okay. And again with factoring, when I think about a quadratic, okay, I want to get it into the form x plus, I'm going to use e and x plus d. Okay? Oh, don't you dare. Don't you dare. Come on. My goodness gracious. X plus e times x plus d equals 0. Okay? Now, just to kind of show you why we're looking, or how to find these e and d, because again, this is the goal, right? If I were to FOIL this thing, you'll see that I get x squared plus dx plus ex plus e times d equal to 0, which simplifies to x squared plus d plus e times x plus e times d equal to 0. Okay? So essentially what we're looking for is if this is what we have, right? We're looking for two values that when I add together I get this coefficient, and when I multiply them together I get this coefficient, or this constant. Okay? So quite simply, if we're going to factor this, Who saw, Mr. Kiefer? Who saw? That's about right. That's about freaking right. And I just said freaking on my recording. I'm sorry. I apologize. Okay, at least it saved most of it. Okay, good. It saved all of it. Thank God. All right. So the whole point of understanding that is now when I go to factor this equation, right, I'm looking for two values, right, that add together to give me 1 and multiply together to give me negative 56. Okay? Now, because the negative 56, right, if I have two numbers and I multiply them together and they end up being a negative, right, doesn't that mean that one's positive, one's negative? Because they were both negative, I would end up with a positive number. They were both positive, I'd end up with a positive number. So when I multiply them out, one has to be positive and one has to be negative. The question is, which one's which? So now let's think about our factors of negative 56. What two numbers can multiply together to give me negative 56? Anyone? What's that? We have 2 and 28. Okay, but if I look at 2 and 28, so let's just say I do negative 28 and positive 2. If I add those together, that gives me negative 26, so that doesn't help. So let's just go about negative 28, and I'm sorry, positive 28 and negative 2, that gives me positive 26. Okay, so all those will multiply together to give me negative 56. They're not going to add together to give me 1. So let's try some different values. What else multiplies to give me negative 56? Guys are killing me here. What two numbers multiply together to give me 56? 8 and 7. 8 times 7 is 56. Common multiplication table, guys. All right. So 8 and 7 multiply together to give me 56, and I know that the difference between them is only 1. Okay, which means if I make one positive, one negative, I can get a positive 1 out of here. Now, since 8's the bigger number, and 1 is positive in this case, I know that 8's going to belong to the positive, and 7's going to belong to the negative. Okay? Now again, I could use the quadratic formula in here, but there's a lot of room for error, especially since we're using the square root, or we have the square root in there, we have plus or minus. There's a lot that kind of goes into it. So if we can factor, I always like to factor first. And part of that reason also is we can use the zero product property. Because what I'm saying when I write this is I've got two quantities that when I multiply them together, they give me 0. What's the only way that that can happen? What's that? Both or 1. If one of them or both of them are 0, I get 0, right? So that's the only way that can happen. So what that means, what that tells me, is that either x plus 8 equals 0 or x minus 7 equals 0. Okay? Which tells me in order for this to work, either x is equal to negative 8 or x is equal to positive 7. Okay? So now we have two potential solutions. what we're going to do is we're going to plug them back in. So we have x is equal to negative 8 or positive 7. Okay? Well, what happens when we plug in negative 8? This becomes negative 8 plus 1, which is equal to negative 7. Likewise, this becomes 2 times negative 8, which is equal to negative 16. So negative 8 in this case will make these two segments negative values, which is not possible. So we cannot use that. Okay? Can x be negative in some cases? Yes, absolutely. Right? But you have to check, because if it makes it an incorrect, or if it makes the segment negative, then you can't use it. Okay? So let's double check 7 now. Okay? Double check 7. So if I'm double checking 7, okay, I get AE is equal to x plus 1, which is equal to 7 plus 1, which is equal to 8. Sorry, that should be AE. I get EB is equal to 2x, which is equal to 2 times 7, which is equal to 14. Okay? Now I still have to check it, right, in this formula. Okay. So I'm going to check by saying, okay, does 8 times 14, does that equal 7 times 16? Well, what's 8 times 14? You want to calculate, please? Eight times 14. 112. And does that equal 7 times 16? Well, 7 times 16 is also 112. So 7 works. So my actual solution is x is equal to 7. Okay. I know that was a lot of work for one problem, right? But part of this was also some Algebra 1 review. So that you guys can remember how to solve quadratic equations, because you'll be doing that in Algebra 2 next year. Okay? Any questions on that part? Okay. I'm going to pause the video for a minute while you guys kind of collect, and we're going to talk about one more thing. Okay? So hang on.